Welcome to my YouTube channel. Today we'll be looking at mathematical induction. So also we'll be talking about the principles, and then we'll be doing some work example. Now, what are the principles of mathematical induction? So if you want to do mathematical induction, you need to understand its principle. So let's get started. The mathematical statement, or the question you want to solve using the mathematical induction, you will name it the P of n. So it is a mathematical statement. You name it P of n. Then for any natural number, n equals 1, 2, 3. So that n that is inside, it is a natural number. It takes value from 1 all the way to infinity, positive infinity. Now, P of n is true for all natural numbers n if the following three steps are satisfied. The first step is show that P of 1 is true. So that is the first step. The first thing you must do is to show that P of 1, the statement is true when n is equals to 1. Then 2, we are going to assume as an inductive hypothesis that P of k is true for some n equals k. So k is an arbitrary number, so we are just going to assume that n is equal to k. Then step 3 is the last one. You are going to use the step 2. You are going to use that assumption in step 2 to prove or to show that P of k plus 1 is true. And once you do that step 3 and you verify that it is true, then the statement is true for any natural number. You see, this is very, very important because sometimes when we solve a question, when we solve mathematical induction, we will just feel like when they do step 1, that is n equals 1, why is it that we didn't do n equals 2, n equals 3, like just do n equals 2 and just say that the statement is true? Because in a way it is true, because you've done 1, you've done 2, maybe you even do 3. But we are proving this thing for set of natural numbers, for all the numbers inside the natural number. So if you want to prove this, you have to convince us that for any number we pick inside that set of natural numbers, there won't be any number that will fail. Meaning all the numbers in the natural number satisfy it. So if you decide to work with fixed numbers like 1, 2, 3, then if I ask you the question that will it work when n is equals to 4, what you've proved can't answer it. You understand? You only say, I think it will work. You are not sure if it will work or not. So that is why we now say, instead of using n equals 2, n equals 3, n equals 4, then just use n equals k. So that k is any number. That k represents any number. It actually represents 2, it represents 3, it represents 4. Then the k plus 1 is the next number after the n equals k. So if n equals 4, then k plus 1 will be n equals 5. You understand? And this is enough. So if you can prove that, if you assume that n equals k, and you show that n equals k plus 1 is also true for the statement, then you've proved it for all the natural numbers. I think that is explanatory enough. Now, let's look at example 1. So we are asked to use the mathematical induction to prove that for all natural numbers, this statement is true. So to start with, solution. So you will say, let the statement be what? P of n. So that is the first step. So step 1 say, you can number it so that you won't forget what you need to do. Step 1, you say let n be equals to 1. You want to prove that the statement is true for 1. So let's do that. To do that, first of all, in this series, this is a series. So 1 is the first term, 3 is the second term, 5 is the third term, like that. And this 2n minus 1 is the nth term. So they are saying the series, if you sum all this up, it will be equals to n squared. So this is the left hand side and this is the right hand side. So to prove n equals 1, you can pick this nth term, because we are dealing with the first term now. So you can pick this 2n minus 1. So that is the left hand side now, which is 2n minus 1. You can put 1 there, minus 1. So this must be equals to the n squared. N squared is 1 squared. So that will give you 2 minus 1 equals 1 squared. 2 minus 1 is 1, then 1 squared. You can 1 squared is actually 1. So you can see that the left hand side is equal to the right hand side. So P of 1 is true. So that is what we've observed. We've observed that P of 1 is true because the left hand side is equal to the right hand side. Now let us continue. Step 2. Step 2 is to assume. So assume P of n is true for n equals k. Assume P of n is true for n equals k. So if this is true, it means that the left hand side will be equal to the right hand side. So that will be 1 plus 3 plus 5 plus dot 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 plus 2k minus 1 equals to k squared. But the question is, why am I writing the whole series? Why don't I just write 2k minus 1 is equals to k squared? Pay attention to this. It is because this is a series, and you know series is the sum of sequence, and series is the sum of sequence. So if I say n equals k now, meaning I'm dealing with the sum of the kth term. The sum of the kth term is not, I'm not considering the kth term. The kth term, look at in this series now, the nth term is 2n, the nth term is 2n minus 1. But the sum of the nth term, is 1 plus 3. The sum of the nth term, you are going to add the first term plus the second term plus the third term. You add everything all the way to the nth term. So that is the sum of the nth term. So that is why it is 1 plus 3 plus 5 all the way to 2k minus 1. So this is the nth term. So when you sum everything to give you the sum of the nth term, so that is why it is like this. It's equals to k squared. So you can name this equation, you can name it 1 because we are going to use it to solve the next one. So step 3, we say let n be equals to k plus 1. So this is the k plus 1 term. So for the left hand side, we'll be looking for the k plus 1, the sum of the k plus 1 term. So to get the sum of the k plus 1 term, you must have, you will add the first term, the second term, the third term, the nth term plus the k plus 1 term. So that will now be 1 plus 3 plus 5 plus dot 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 plus the kth term is 2k minus 1, and then the k plus 1 term will be 2. No, the nth term is 2n minus 1. So the k plus 1 term will be 2 into k plus 1 minus 1. So you can just write that k plus 1 minus 1. So this, so you know, on the other side, on the right hand side of the statement, we have is equal to n squared. So we are going to replace, we have n squared, so we are saying n is equals to k plus 1. So we get k plus 1 all squared. So this is the right hand side and this is the left hand side. So moving on, so this part now, this part will be equal to, this first part now is the sum of the nth term, and that is what you have above here. It is equals to k squared. So you write k squared here, plus you can write this kn plus 1, then minus 1 equals to k plus 1 squared. So we want to prove that the left hand side is equals to the right hand side. So let's focus on the left hand side. So we have k squared plus, open that bracket, you have 2k plus 2 minus 1 equals to k plus 1 squared. So you have k squared plus 2k plus 1 equals to k plus 1 all squared. So this k plus 1, k squared plus, you can factorize this, that will give you k, then also k. So you can think of two numbers that you will times that will give you 1 if you add them to give you 2. That is plus 1, and it is 1 times 1 that will give you 1, and 1 plus 1 will give you 2. So it is plus 1 plus 1, and this is actually equals to, if you times this to get k plus 1 squared equals to k plus 1 squared. So this is it. So this is to show that p of k is true. So p of k plus 1 is true. You can see that p of k plus 1 is true. So we can just say hence p of n is true for what? For any natural number. So that is it. It's as simple as that. So example 2 says that we should use mathematical induction to prove for all natural numbers that this statement is true. So solution. Just say that, start with, let the statement be p of n. So the whole statement has been represented with p of n. Now, what is step 1? Step 1 is to prove that the statement is true for n equals 1. So for n equals 1, you can just use the n term. So we have 1 into 1 plus 1. We want to show that is equals to 1 over 3 into 1, 1 plus 1, then 1 plus 2. This is 1 times 2 plus 1 over 3 times 1 times 2 times 3. So this is 3, this is 2. 3 cancel 3, you get 1 times 2, which is 2. So you could see that the left hand side is equal to the right hand side. So we say that p of 1 is true. So the next thing is to solve, is to assume, step 2. So assume p of n is true for n equals k. So if you assume this, so we are going to have 1 times 2 plus 2 times 3 plus 3 times 4 plus dot dot plus k into k plus 1 equals 1 over 3 k into k plus 1 times k plus 2. So this is the left side, is the right side. We call this equation 1 because we are going to use it in the next question, in the next step. Step 3, now say let n be equals to k plus 1. So we want to prove that this is also true. So remember what I explained in example 1. This is the nth term. So if you are looking for this is the sum of the nth term, like step 2. The left hand side is the sum of the nth term. So to get the n equals k plus 1 term, so you need, for the left hand side, you do the sum of the k plus 1 term. So that will be 1 into 2 plus 2 times 3 plus 3 times 4 plus dot dot plus k into k plus 1. This is the sum of the nth term, plus you will now add the k plus 1 term. So this one will be, you know, the nth term is defined to be n into n plus 1 by the definition. Let me go up so that we can see that from the it is n into n plus 1. So it is that one you substitute the k plus 1. So if you put k plus 1, you get k plus 1 into k plus 1, or k plus 1 plus 1 plus 1 sorry, so you get k plus 1 into k plus 1 plus 1. So that is what you get. So on the other side now, the definition is, I think, is 1 over 3 n k plus 1 n into n plus 1. So you just replace the n by k plus 1. So you get 1 over 3. Here becomes k plus 1, and here you get you get k plus 1 plus 1, because these are your n now. Then you also get k plus 1 plus 2. Okay, so let's move on. So what are we doing now? So this whole part, this is the sum of the nth term. We have it at the top here. It is equal to this. So you come here and replace it by that. 1 over 3 k into k plus 1, then k plus 2. So this is the sum of the nth. The sum of the nth term is equal to this. Then you can just write this one back. You have k plus 1. So when you add 1 plus 1, you get 2. So that is k plus 2. So this is the left hand side now. So for the right hand side, we get 1 over 3 k plus 1, and then k plus 2 times k plus 3. So this is what we want to prove. We want to prove that the left hand side is equal to the right hand side. So I think at this point we should write out the right hand side. Right hand side is 1 over 3k into k plus 1, then k plus 2 plus k plus 1, then times k plus 2. So this is what we want to simplify to get this right hand side. So to solve this, these 3 is at the denominator here. It's multiplying this whole thing, so it's at the denominator. The denominator of this is 1. So you can look for the LCM. So the LCM of 3 and 1 is 3. 3 into 3, you get 1. So that is k into k plus 1, then k plus 2 plus 3 with times this. That is 3 into k plus 1, then k plus 2. Now you can factorize what is common at the numerator. I think k plus 1 is common and k plus 2 is also common. So if you bring out k plus 1 and k plus 2, you'll be left with k there. Then on this other side, you'll be left with 3. So everything is being divided by 3. So remember, this is your left hand side. So I think we are done simplifying that. So let's look at the right hand side. Look at the right hand side. So the right hand side is also equals to 1 over 3. So this is also equals to 1 over 3. It's actually the same as the, let me just write it for formalities. So this is what, this one is the right hand side. So what we are saying is that the left hand side is now equals to the right hand side. So with that, we've proved that k plus 1 is true. So you can see that the condition of the principle has been satisfied. So you just conclude that p of n is true for any natural number. So that is it. Let's look at example 3. So we are asked to use the mathematical induction to prove that for all natural number, 9 is a factor of 5 raised to the power of 2n plus 3n minus 1. So you can observe that example 1 and example 2, they are example 1 and example 2, they are kind of similar, but example 3 is different because we want to use the mathematical induction to prove that something is a factor of the other. So before we start example 3, you need to understand what is the meaning of a factor and what does it mean for 9 to be a factor of a number. So for 9 to be a factor of a number, that number can be expressed as a product of 9 and any number, or we can say that 9 should be able to divide that number. 9 is a factor of 27 because 9 can divide 27. 9 is a factor of 18 because 9 can divide 18. And also 18 can be expressed as a product of 9 times a number. The reason why 9 cannot divide 10 is because you can't express 10 as a product of 9 and a particular. You can't find a natural number that you will use to times 10 that will give you 9. That you express 9 as a product of. 9 times what will give you 9? You can't, we give you 10. Yes, 9 times what will give you 10? It's not possible. You can't get a natural number that will satisfy that condition. That is why it is not a factor of 10. So let's see how this works. So solution, we do the same thing. We say let the statement be P of n. Step 1. So we say let n be equals to 1. So for n equals 1, we have, let's see whether the question is a factor of 9. So we have 5 raised to the power of 2 times 1 plus 3 times 1 minus 1. 5 raised to the power of that is 25 plus 3 minus 1. So this is 2. That is 27. So this is a factor of 9 because 27 can be expressed as product of 9 times a number. So it's a factor of 9. So step 2 is to assume that n equals k is true. So you say assume n equals k is what? Is true. So if this statement is true, it means that 5(2k) plus 3k minus 1 must be equal to 9 times a natural number. So you can just say m is coming from a natural number. M is a set of, it's coming from the set of natural number. So yes, let's continue. So you can also call this, I need to name it now. You can call this equation 1 because you will need it for the next for what we have to, for the next step. Yes, step 3. Step 3 is to prove that n equals to k plus 1 is true. So to do that, anywhere we see n in the formula, we replace it by k plus 1. We have 5 into k plus 1 plus 3 into k plus 1 minus 1. So we want to prove that this expression 2 is equal to it will be equals to a product of 9 and a particular number. That's what we want to show. So let's see how it works. So let's open this bracket at the power. We have 2k plus 2 plus, here will give you 3k plus 3 minus 1. This 2k, here will give you dot 5 raised to the power of 2 plus 3k plus 2. Okay, so this is what we get. So remember that in the theorem or in the principle, you will need to use this first step. So what do we need to pick from this first step? How are we going to use it in this case? So let's try and get rid of the power. So in this expression, we have 5 raised to the power of 2k. This 2k part, let's try and get rid of it. So using this equation 1, so you can just say from 1. So from 1, we have 2k plus 3k minus 1 is equals to 9m. So let's make 2k the subject of formula. You get 9m minus 3k plus 1. So let's this go and replace that. We have 5 raised to the power of 2 into k plus 1 plus 3 into k plus 1 minus 1. So what will this be equals to now? So the whole of this will be replaced by this. So you get 9m minus 3k plus 1 raised to the power of 5 raised to the power of 2 plus 3k plus 2. Alright, so first, well, let me just rewrite this. 5 raised to the power of 2 is 25. Then you have 3k plus 2. So this will be 9 times 25m minus 3 times that is 75k plus 25 plus 3k plus 2. You don't have to multiply this, just leave it like that. So but if you want to, there is no problem. I just said you don't have to multiply that. So if you add this to this, you have minus 72k. If you add this to this, you will get 27. So I think you can be able to factorize 9 from here. So if you bring out 9, you get 25m minus 8k plus 3. So you can see that the whole of this, that is 52k plus 1 plus 3k plus 1 can be represented as a product of 9 times a number. You can represent the whole of that as p, and just say where p is equal to 25m minus 8k plus. It's not really necessary, but so with this now, this is a factor. This expression on the left is a factor. 9 is a factor of it, because you can see that you can represent the whole thing on the left now as a product of 9 and a number. So 9 can actually divide it, because if 9 divide this, you will get p. So 9 is also a factor of it. So what you have to do, we are done. So you are just to conclude that p of k plus 1 is what? Is true. Is true. So hence p of n is true for any natural number. Okay, thank you very much for watching this video to the end. Before you leave this channel, make sure you subscribe and click the like button. Thank you very much. Also share this video to your friends so that they can also watch and learn. Thank you.